Server-side request forgery, SSRF, attacks with Dave.
Hello everyone, and welcome back to Dave_official. In today's lesson, we're going to explore one of the most dangerous and impactful web security vulnerabilities, server-side request forgery, commonly known as SSRF. SSRF is a vulnerability that allows an attacker to trick a web server into making requests on their behalf. This can lead to unauthorized access to internal systems, sensitive data exposure, cloud metadata theft, and even further attacks on back-end infrastructure. In this lesson, you will learn, Small Blue Diamond, what SSRF is and how it works. Small Blue Diamond, the real-world impact of SSRF attacks. Small Blue Diamond, common SSRF attack scenarios and techniques. Small Blue Diamond, best practices for preventing and mitigating SSRF vulnerabilities. Whether you're an aspiring ethical hacker, bug bounty hunter, penetration tester, or cybersecurity enthusiast, understanding SSRF is an essential skill in modern web security. So, without further ado, let's dive into Lesson 4, Server-Side Request Forgery, SSRF, Attacks. Direct hit. Let's get started. Fire.
What is SSRF? Server-side request forgery is a web security vulnerability that allows an attacker to cause the server-side application to make requests to an unintended location. In a typical SSRF attack, the attacker might cause the server to make a connection to internal-only services within the organization's infrastructure. In other cases, they may be able to force the server to connect to arbitrary external systems. This could leak sensitive data, such as authorization credentials. What is the impact of SSRF attacks? A successful SSRF attack can often result in unauthorized actions or access to data within the organization. This can be in the vulnerable application or on other back-end systems that the application can communicate with. In some situations, the SSRF vulnerability might allow an attacker to perform arbitrary command execution. An SSRF exploit that causes connections to external third-party systems might result in malicious onward attacks. These can appear to originate from the organization hosting the vulnerable application.
What is common SSRF attacks? SSRF attacks often exploit trust relationships to escalate an attack from the vulnerable application and perform unauthorized actions. These trust relationships might exist in relation to the server or in relation to other back-end systems within the same organization. What is SSRF attacks against the server? In an SSRF attack against the server, the attacker causes the application to make an HTTP request back to the server that is hosting the application via its loopback network interface. This typically involves supplying a URL with a hostname like 127.0.0.1, a reserved IP address that points to the loopback adapter, or localhost, a commonly used name for the same adapter. For example, imagine a shopping application that lets the user view whether an item is in stock in a particular store. To provide the stock information, the application must query various backend REST APIs. It does this by passing the URL to the relevant backend API endpoint via a front-end HTTP request. When a user views the stock status for an item, their browser makes the following request: post/product/stock HTTP 1.0. Content type: application/xwww formerly encoded. Content length: 118. Stock API =http://stock.wellightashop.net 8080/product/stock/check% 3f product ID % 3d6% 26 stored % 3d1. This causes the server to make a request to the specified URL, retrieve the stock status, and return this to the user. In this example, an attacker can modify the request to specify a URL local to the server, post/product/stock HTTP 1.0. Content type: application/xwww formerly encoded. Content length: 118. Stock API =HTTP://localhost admin. The server fetches the contents of the /admin URL and returns it to the user. An attacker can visit the /admin URL, but the administrative functionality is normally only accessible to authenticated users. This means an attacker won't see anything of interest. However, if the request to the /admin URL comes from the local machine, the normal access controls are bypassed. The application grants full access to the administrative functionality because the request appears to originate from a trusted location. Why do applications behave in this way and implicitly trust requests that come from the local machine? This can arise for various reasons. The access control check might be implemented in a different component that sits in front of the application server. When a connection is made back to the server, the check is bypassed. For disaster recovery purposes, the application might allow administrative access without logging in to any user coming from the local machine. This provides a way for an administrator to recover the system if they lose their credentials. This assumes that only a fully trusted user would come directly from the server. The administrative interface might listen on a different port number to the main application and might not be reachable directly by users. These kind of trust relationships, where requests originating from the local machine are handled differently than ordinary requests, often make SSRF into a critical vulnerability. What is SSRF attacks against other backend systems? In some cases, the application server is able to interact with backend systems that are not directly reachable by users. These systems often have non-routable private IP addresses. The backend systems are normally protected by the network topology, so they often have a weaker security posture. In many cases, internal backend systems contain sensitive functionality that can be accessed without authentication by anyone who is able to interact with the systems. In the previous example, imagine there is an administrative interface at the backend URL http://192.168.0.68/admin. An attacker can submit the following request to exploit the SSRF vulnerability and access the administrative interface: post/product/stock http://1. 0. Content type: application/xwww formal encoded. Content length: 118. Stock API =192.168.0.68/admin. What is circumventing common SSRF defenses? It is common to see applications containing SSRF behavior together with defenses aimed at preventing malicious exploitation. Often, these defenses can be circumvented. What is SSRF with blacklist-based input filters? Some applications block input containing hostnames like 127.0.0.1 and localhost, or sensitive URLs like /admin. In this situation, you can often circumvent the filter using the following techniques. Use an alternative IP representation of 127.0.0.1, such as 2130706433, 0177000000001, or 127.1. Register your own domain name that resolves to 127.0.0.1. You can use spoofed.burpcollaborator.net for this purpose. Obfuscate block strings using URL encoding or case variation. Provide a URL that you control, which redirects to the target URL. Try using different redirect codes as well as different protocols for the target URL. For example, switching from an HTTP to HTTPS URL during the redirect has been shown to bypass some anti-SSRF filters. What is SSRF with whitelist-based input filters? Some applications only allow inputs that match a whitelist of permitted values. The filter may look for a match at the beginning of the input or contained within it. You may be able to bypass this filter by exploiting inconsistencies in URL parsing. The URL specification contains a number of features that are likely to be overlooked when URLs implement ad hoc parsing and validation using this method. You can embed credentials in a URL before the hostname using the character. For example, https://expected-host, fake password at evil host. You can use the hash character to indicate a URL fragment. For example, https://evilhost hash expected host. You can leverage the DNS naming hierarchy to place required input into a fully qualified DNS name that you control. For example, https://expected-host.evil-host. You can URL encode characters to confuse the URL parsing code. This is particularly useful if the code that implements the filter handles URL encoded characters differently than the code that performs the backend HTTP request. You can also try double encoding characters. Some servers recursively URL decode the input they receive, which can lead to further discrepancies. You can use combinations of these techniques together. What is bypassing SSRF filters via open redirection? It is sometimes possible to bypass filter-based defenses by exploiting an open redirection vulnerability. In the previous example, imagine the user-submitted URL is strictly validated to prevent malicious exploitation of the SSRF behavior. However, the application whose URLs are allowed contains an open redirection vulnerability. Provided the API used to make the backend HTTP request supports redirections, you can construct a URL that satisfies the filter and results in a redirected request to the desired backend target. For example, the application contains an open redirection vulnerability in which you can leverage the open redirection vulnerability to bypass the URL filter and exploit the SSRF vulnerability as follows: post/product/stock HTTP 1.0. Content type: application/xwww formerly encoded. Content length: 118. Stock API =HTTP. //welligtoshop.net/product/next product ? Current producted =6 path HTTP. //192.168. 0.68/admin. This SSRF exploit works because the application first validates that the supplied stock API URL is on an allowed domain, which it is. The application then requests the supplied URL, which triggers the open redirection. It follows the redirection and makes a request to the internal URL of the attacker's choosing. What is blind SSRF vulnerabilities? Blind SSRF vulnerabilities occur if you can cause an application to issue a backend HTTP request to a supplied URL, but the response from the backend request is not returned in the application's front-end response. Blind SSRF is harder to exploit, but sometimes leads to full remote code execution on the server or other backend components. What is the impact of blind SSRF vulnerabilities? The impact of blind SSRF vulnerabilities is often lower than fully informed SSRF vulnerabilities because of their one-way nature. They cannot be trivially exploited to retrieve sensitive data from backend systems, although in some situations they can be exploited to achieve full remote code execution. How to find and exploit blind SSRF vulnerabilities? The most reliable way to detect blind SSRF vulnerabilities is using out-of-band OWASP techniques. This involves attempting to trigger an HTTP request to an external system that you control and monitoring for network interactions with that system. The easiest and most effective way to use out-of-band techniques is using Burp Collaborator. You can use Burp Collaborator to generate unique domain names, send these in payloads to the application, and monitor for any interaction with those domains. If an incoming HTTP request is observed coming from the application, then it is vulnerable to SSRF. Note: it is common when testing for SSRF vulnerabilities to observe a DNS lookup for the supplied collaborator domain, but no subsequent HTTP request. This typically happens because the application attempted to make an HTTP request to the domain, which caused the initial DNS lookup, but the actual HTTP request was blocked by network-level filtering. It is relatively common for infrastructure to allow outbound DNS traffic, since this is needed for so many purposes, but block HTTP connections to unexpected destinations. Simply identifying a blind SSRF vulnerability that can trigger out-of-band HTTP requests doesn't in itself provide a route to exploitability. Since you cannot view the response from the backend request, the behavior can't be used to explore content on systems that the application server can reach. However, it can still be leveraged to probe for other vulnerabilities on the server itself or on other backend systems. You can blindly sweep the internal IP address space, sending payloads designed to detect well-known vulnerabilities. If those payloads also employ blind out-of-band techniques, then you might uncover a critical vulnerability on an unpatched internal server. Finding hidden attack surface for SSRF vulnerabilities. Many server-side request forgery vulnerabilities are easy to find because the application's normal traffic involves request parameters containing full URLs. Other examples of SSRF are harder to locate. Partial URLs in requests. Sometimes, an application places only a hostname or part of a URL path into request parameters. The value submitted is then incorporated server-side into a full URL that is requested. If the value is readily recognized as a hostname or URL path, the potential attack surface might be obvious. However, exploitability as full SSRF might be limited because you do not control the entire URL that gets requested. URLs within data formats. Some applications transmit data in formats with a specification that allows the inclusion of URLs that might get requested by the data parser for the format. An obvious example of this is the XML data format, which has been widely used in web applications to transmit structured data from the client to the server. When an application accepts data in XML format and parses it, it might be vulnerable to XXE injection. It might also be vulnerable to SSRF via XXE. We'll cover this in more detail when we look at XXE injection vulnerabilities. SSRF via the referrer header. Some applications use server-side analytics software to track visitors. This software often logs the referrer header in requests so it can track incoming links. Often the analytics software visits any third-party URLs that appear in the referrer header. This is typically done to analyze the contents of referring sites, including the anchor text that is used in the incoming links. As a result, the referrer header is often a useful attack surface for SSRF vulnerabilities. Awesome! You've completed Lesson 4 on Server-Side Request Forgery, or SSRF. I hope Dave helped you understand how SSRF vulnerabilities work, how attackers exploit them, and why they're such an important part of web security testing. If you enjoyed this lesson and found it helpful, don't forget to like the video, subscribe to the channel, and turn on notifications so you never miss future cybersecurity content. This is Dave, signing off. Thanks for watching, and I'll see you in the next lesson. Stay safe, stay ethical, and keep learning cybersecurity.